participants also from outside this room. We have the pleasure to announce Mohan Kambampati from the Friends University in Wichita.
Yes.
And he will give us some insights about simulated mineral exploration project. We are keen to hear
Thank you.
your presentation.
Thank
The
you.
floor is yours, and
Thanks.
all the best.
Okay.
Thank you.
Okay, this is simulated mineral exploration, and okay, that is the title, and that is me, who's a, and actually, that is me really, who is a retired faculty member from the Friends University in Wichita, Kansas. Okay. Briefly, my background is, okay, I worked for the Geological Survey of India for 10 years, and I was involved in exploration projects for copper, coal, iron ore, and bauxite. So this presentation is divided into three parts. One is the background of mineral exploration, and then the second is the simulation, and the third is the project-based teaching and project-based learning. Now, then, okay, types of mineral deposits. Okay. There are different types of mineral deposits, different classifications of mineral deposits. I am using the word mineral deposits and ore deposits. So the mineral deposits and ore, these are different classifications. I am using this word because the minerals deposits and ore deposits, the convention is metallic minerals such as copper, lead, zinc. They are called ores. Non-metallic minerals like a coal, limestone, and others, they are called mineral deposits. So we don't say coal ore, we will say core. Coal ore. We will say coal deposit, like that one. Then, so one is, now we will go to this this mineral deposit word is a, I can't see this. The mineral deposit is the natural occurring metallic ore deposit. You can see. Ore may be defined as a naturally occurring ore may be defined as a naturally occurring metallic mineral. So that is the ore definition, metallic resource. Oh, I can see here. The ore may be defined as a naturally occurring metallic resource, which can profitably be mined. The key word here is profitably mined. So even if we know that there is an ore, let's say copper ore below the ground and all that, if it is not profitably mined, how is that profitably mined? It is the quantity, there should be enough quantity of it, and the grade. These two combined is profitably mined. Mining is very expensive process. So if it's not justifies it, it won't be profitable. That's why it is there. And then now we call energy resource. So now we will come to the ore deposits. The ore deposits are classified as metallic resources, energy resources. Energy resources, a good example is the uranium and the thorium. So uranium and thorium, now monzonite placer deposits are an important source of thorium, which can be converted to uranium to use an energy source. So those are the two classifications. Now, to understand the origin of ore deposits, such as copper, lead, zinc, platinum, and many more, we must understand Bowen's reaction series. So the whole origin of ore deposits can be explained through Bowen's reaction series. We will learn more about through the Bowen's reaction series, but for that it is important. Okay, this is famous Bowen's reaction series picture. All geology students must have studied this. All. This is a very important slide. Now, this slide tells us two stories. One story is the temperature regimes, highest temperature as magma is cooling, magma is here. As magma is cooling, you get highest temperature to lower temperature 650 degrees centigrade. Correspondingly, at higher temperature, we get the rocks, ultramafic rocks. Those rocks are comatite and peridotite. Now there's a spelling mistake here, ultramafic, but I have to take what the original tells. So we did not change anything. Uh, so ultramafic rocks are comatite and peridotite. Comatite is an extrusive rock, peridotite is an intrusive rock. Then as the temperature comes down, various rocks are formed. And then slightly lower that is the basaltic rocks, basalt and gabbro. Much lower andesitic rocks, andesite and diorite. And then at the end stage, as it reaches to around 650 degrees centigrade, you have the granitic rock, which is rhyolite and granite. So these combination is one story. The other story is the mineral formations. Okay, after all, rock is an aggregate of minerals. So this is discontinuous series. This is a continuous series. What is discontinuous series? So as the temperature is coming down, the first mineral to form is the olivine, iron magnesium silicate. So then the comes, so the olivine, it takes all the, it's mostly magnesium. It consumes all the magnesium, not so far, a little bit left, but olivine, and it says, okay, my job is done. I'm going down. So that it goes, settles down in the magma chamber. Next one is pyroxene. It's the same thing, olivine magnesium silicate, but here iron magnesium silicate, but here magnesium is the predominant, and here iron is the predominant. That form. The next mineral forms is amphibole. Amphibole also is iron magnesium silicate, but in the amphibole there is more hydrous content. So it is more water in that. So then comes biotite, potassium feldspar. So each is independent. That is why discontinuous series. This continuous series is only one mineral forms, plagioclase feldspar. Plagioclase feldspar. Though here it starts with high calcium rich, and as the temperature is coming down, medium, medium, and then finally it comes to sodium rich feldspar. Then we have a potassium feldspar. It's an independent thing. I'm not going to join with you. I have my own freedom. So potassium feldspar, muscovite, and quartz. This is the second story. This is the story that formed on the Bowen's reaction series, and we are going to depend to some extent on this series. Yeah. So now, where is magma produced? Okay. Mr. Bowen. So as we go down the earth, temperature and pressure increases. As they are increasing, so for example, many of you know that the earth is divided into crust, mantle, core, outer solid core, and inner liquid core. So as the temperature is increasing in the mantle, upper mantle starts melting, partial melting. That is how the magma is generated. So, okay, relationship between the Bowen's reaction series and mineral exploration. Like I said, it's important concept. So what is the relationship between this Bowen's reaction series and the mineral exploration? We will see it now. Understanding the sequence of mineral formation is vital. Okay. Vital for identifying ore deposit. For example, the earliest formed rock are ultramafic rocks, and then the ultramafic rocks are peridotite is the host. One of the rocks that forms at the ultramafic is called peridotite. That is the host for many, many valuable ore deposits, platinum, core, nickel, and non-ore deposits, diamond, talc, chrysotile, asbestos, like that. That is the formation, that is the relationship between the, Burns reaction series and mineral formation. That is not the only there. This is, for example, you come to granitic rocks. Granitic rocks are host for uh, copper, lead, zinc. So that is, and as the, for example, the medium temperature, the andesitic rock, they are also host for copper, lead, zinc. So that is how the relationship between those two. And then we have hydrothermal deposit. This at the end stage here is where the hydrothermal solutions are left over after the formation of all the rocks. Though the average stages, at the very end stage of the remnant solutions, hydrothermal solutions are rich in ore minerals such as copper, zinc, tungsten, molybdenum. This is like pina colada, that all those juices are there. But like that, this one. Um, and then skarn and porphyritic deposits. They are the different rock types there. No, hydrothermal. These hydrothermal solutions will, with all its concentration of minerals, it will intrude into the country rock or host rock. Okay. And there it deposits copper mineralization, in our case, copper mineralization, but it will deposit any other minerals it is carrying. And in those fractures and veins and patches. So because the last stage rocks are granitic rock, that's why I said in the granitic rock, copper and lead, zinc are the uh, present there. So then this is the repetition, what I said. They are formed at the stage of Bowen's reaction series. Mineralization occurs as different sizes of veins and patches. Thus, an exploration geologist working for platinum or chromite will explore in peridotite rocks, and copper and other base metals, he will concentrate on the granitic rocks. Then there are other types of mineral deposits. Placer deposits. Placer deposits are the ones, the water that is passing through the rocks, it will dissolve the high specific gravity minerals like gold and diamond. And it sticks up and then deposits in the beach sands or in the bars, in the channels. That is why we can famous uh, panning for the gold. That is what it is. That is the panning. Those are the placer deposits. They are important for certain extent. Placer deposits are important in mineral exploration. Then metamorphic mineral deposits. The metamorphic mineral deposits are high temperature. Metamorphism is high temperature and pressure issues. So there, these metamorphic mineral deposits takes place. They are like ruby red, or her lips emerald green, or her eyes, like that. If I have to buy for rubies and emeralds for my wife, I have to do the exploration in the metamorphic rock. And bedded and layered deposit. But a good example of bedded deposit is coal. Coal occurs as seams. Okay, and layer deposits, and then the bauxite layers. So those are those three different kinds. Skarn and porphyry deposit. Skarn and porphyry deposits are tricky. The hydrothermal solutions, their deposits the mineral in as a porphyry. That means in the rock it is disseminated in all over this place and all. So they are porphyry deposits, but their grade is less. It's only 0.3% copper. But the advantage is they are spread over a large area. So some exploration companies will say, what the heck, we will mine all the whole thing and then we can get more copper. So that is what porphyry deposits are. Then what is mineral exploration? Okay. Mineral exploration is the method of finding mineable minerals, okay, mineable mineral deposits in the ground, or to examine possibilities of such mineralization. The key word here is finding mineable mineral deposit. We can find mineral deposits in the ground, but if their grade is not high and if the quantity is not large, then what is the point? It cannot be mined. Like I said, mining is very expensive process, and you need to have plenty of ore and plenty of grade, good grade. So that is what the mineral exploration, mineral exploration is looking for that qualifications. Say again, what is mineral exploration? Like I told, if the target is to find platinum or chromite, he will do the exploration in ultramafic rocks. If the target is to find copper, lead, zinc, base metals, he will do exploration in the granitic rocks. Okay, then steps of target generation. Let us say the exploration is for copper. Okay. So if it is for copper, the initial explorations begins with the appraisal of known copper bearing areas. Okay. Let's say a company hires me and Mohan, go and find out where we can find the copper deposits. Okay, not only me, there will be a team of geologists. So what is the first task? Initial begins appraisal of known copper bearing area. That means the mapping is done. Mapping has got two types of things. One is a regional mapping, broad, general. That geologists, they will explain what indications are there for the minerals, what kind of minerals are likely to be present, and those aspects of it will be done. The second one is the detailed mapping. Okay. So I will pick up the appropriate maps are studied for that one. The maps are available in libraries and in the geological surveys, like that one, and universities. Yeah. So those maps will be studied. So the initial begin appropriate known copper bearing areas and the maps. If previous exploration was conducted in the area, their reports are to be studied. There could be exploration in the previously done. So those exploration, they might have abandoned it because it's not worth during at that time. I'll come to that point a couple of times. At that time, those are worth exploring and that mineable one. But now, with the price of the copper, the demand or something, it is not a necessarily good one. So the exploration conducted in the area, they would have prepared a report. It is important to study those reports. Detailed exploration mapping must be conducted, paying attention to GOSAN, and I'll tell you what is GOSAN. So detailed exploration mapping. So now comes the real task. No more coffee drinking, computer browsing thing. I have to pack up and go into the field. Sulfide deposit. Now, what is GOSAN? That they are very important. sulfide deposit, let me make one thing clear. When I say copper ore, that it doesn't occur like just a bunch of copper patches or veins or something. What we are looking for is copper sulfide, which is a chalcopyrite or chalcopyrite. Then, or it is a, if the exploration is for zinc, it is sphalerite, zinc sulfide. That one. So that these and so say in the chalcopyrite, which is a copper iron sulfide, it is leached out. One time they are on the pretty surface level, shallow level. It is leached because of the water, rain, and all that, and and that it leaves the material stuff that leaves out. That is called gosan. The gosan is a very important guide for a geologist. So that looks very beautiful colors like red and violet and green and all those. And then the gosan is there. That is an indication that one time there must have been copper around this area. So then, of course, the aerial photos and satellite images are to be studied. The boson zones are seen prominently in the satellite images. And then preliminary geophysical and geochemical surveys are to be conducted. That nails down to some extent. Then what? Same data may be viewed differently by different exploration agencies with a change of time. An area which was considered unexplorable one time may be unexplorable today because it is the changed economic condition, changed demand or anything. Again, let's come back to the example of copper. So the copper now is not big demand. So what is not worthy of exploration 10 years ago is maybe worthy of exploration now because of the price of the copper and all that. That is why probably you heard that their copper is being stolen from houses and um, when they dump the copper tubes and all that, they are all stolen and sold. So the target area that has been determined needs further exploration to build more confidence. So these the steps that I narrated 1 to 6, they are leading into surface exploration. So now it's still not very positive. So to be very positive, so we have to do some more preliminary geochemical and geophysical surveys. This accomplished through detailed geophysical and geochemical surveys. However, we still cannot see the metal, see the ore. Please keep in mind, we cannot see the ore yet. Okay. Now we will go to section 2, simulation of mineral exploration. That is the key for that. This is what my presentation's importance, simulation of mineral exploration. Then advanced technologies, not necessarily in the geology field, various advanced technologies may be creating demand for those base metals. So far whatever I talked about is a prelude to this section. Okay. In regular classrooms, and generally, I'm generalizing here, the mineral exploration in the chapter in the book stops so far whatever I have told. But that is not the end of it. There is more for the mineral exploration. That is the theme of my presentation here. In the real world, there's more exploration and to prepare the students for the real world situations. The ultimate goal of exploration is how much ore, again, the point is how much ore is there under the ground and what grade is there. So this section here now deals with core drilling, core sampling, weighted average, and then reserve calculation. That's the goal, reserve calculation, that's the bottom line. So for that, we need to do the core drilling and see the ore with the naked eye and do the sampling. Then with that data, we calculate the reserve calculation. Yeah. Core drilling, as they say, seeing is believing. And I said geochemical prospecting and geophysical prospecting only confirms that there may be a mineralized zone there. The only way we can see that mineralization is by drilling. That is the only tool to define outlines of the deposit. Okay, what is diamond core drilling? Now, this is a picture. What is core drilling? Now, this is a core barrel. Imagine by hand as a core barrel. Okay. And at the end of the core barrel, there is a bit, core bit or diamond bit is joined. We call them diamond bit. They are not real diamonds. They are only artificial diamonds because diamond is the strongest mineral. That is the only one which can drill through the core. Okay. So that is core drilling there. That is bit. And as the drilling is continuing, goes on, for example, as the drilling is progressing, the core will get into my core barrel. You get a barrel that comes on like that. The drill bit is attached to the drill barrel. That's what I explained. Drill barrel, the bit rotates at high speed, cutting the rock. And because it is rotating at a very high speed, it generates very heat. And then in order to cool down, then the drilling crew will send water there. So that is how the drilling happens. For soft rocks, okay, when there is no diamond drilling is needed, it is not done by drilling. For soft rocks, less hard minerals used in the impregnated, and that is used as a core, as a bit. Geologists based on, okay, so in the earlier section, I went through, let's see if we can get back there. Okay, here, these are the ones. Steps of target generation, all these steps, okay. Drilling as progresses, so okay, that's one. As the drilling progresses, the drill crew will drill about 4 to 6 feet of core, and then they will put them in the core boxes, and they will bring those boxes to the geologist. So the geologist will be looking for the core logging. Core logging is an important step. The geologist's role, I have to point out, geologist's role here is very important in the mineral exploration. He has to make very crucial decisions. Okay. So he has to examine the core very carefully and see that. The drilled core is stored in core boxes, geologist logs them. Sometimes, instead of complete core, you may get only pieces, crumpled pieces of that. What does that indicate? That indicates that the rock there is, because of the fault zones or fault or something, the core is not complete there. It's all broken pieces coming up. So at the anticipated of those, now this is another crucial stage is geologist has to get as much information as possible. He needs to decide the first borehole. That's a major decision. So he has to log it very carefully and records in many details as possible to do that. Core sampling and weighted average. Okay. The mineralized core must be okay. So the mineralized core, I'll use this for now, but this is not what I impart. This is for the simulation purposes. Let's say, actually this core size for mineral exploration is very small. I got this from my geology department. I really don't know why they drilled this one. There could be some reason. So, but the core, real core, comes in. It will be almost this size or slightly less than that one. So on the mineralized core must be split. So okay, I'm looking at the core. There are various mineralized zones. I'll come to that and all. So based on the observation, so this is unmineralized rock. Unmineralized rock. These are the various mineralizations. Okay. By looking at it, I see that this is one grade. Just like you're having patches of salt chalcopyrite. This is a big chunk, big patch of mineralization. Again, please remember, this is not a patch of copper metal. It is a patch of copper ore. Ore means, and the ore is chalcopyrite and surrounding country rock. They are combined ore. So then that is where, oh, there's a lot of chalcopyrite here. So I'm going to divide into another zone. So then another little less, little less, little less. So I do that one. So what I get is, no, this is the picture I get. So this is, okay, this is this. So I looked at it. This is our unmineralized core, unmineralized rock. When I look at, okay, there's quite a few patches of chalcopyrite, and this is thick, I said, and these are the things. No. So I will demarcate into different samples, okay, and then I'll get the sample crushed and the powder, and that sample is sent for analysis. Now, one question is, because we need the average ore, but otherwise we need for calculation of reserves, we need the average of this ore in this borehole. This is just one borehole. So this is there. So how do we get the average? It is not arithmetic average. If you do arithmetic average, for example, this 7% copper and 0.5% copper, it's all combines into one. So the value of this copper is diminished because of the arithmetic average. So what we call is weighted average. Okay. What is weighted average? We have to give prominence for this one, recognition on only on that thick 7% copper. This is after we get the analysis. First, I sampled this portion, this portion, this portion, and got the analysis. So the 7% copper is this much. 0.8% is this. If you average what is happening, 7% is watered down. So we have something called weighted average. Weighted average is sum of sample width times weight. Weight is nothing but mineral percentage. These are the weights. Okay. And so weighted average is sum of samples, sample width times weight divided by the sum of weights. This is the information we got. So you multiply the inches by size times weight, percentage of copper, you get this. Okay. And you add up all these things. This is the sum of weighted average weights, and then the sum of percentage. So to tell again, weighted average sum of sample widths times weight, copper percentage, and then we get 30.8% to 30.8, and then sum of the weights, this one, 30.8 divided by 11 is weighted average. So that is the 2.8% copper. There is a 2.8% copper in this thing, average. Okay, good. For the reserve calculation, I got one subsequent borehole. Okay. I cannot calculate the reserve with one borehole. I need more boreholes to find out the uh, ore and also to get the three-dimensional picture. So, so a drilling hole, that is so I have to select some other borehole. I have to not select. I have to calculate, or I have to imagine where other boreholes will be drilled. You will see in a minute. Then hydrothermal vein deposits is very difficult to stop where the drilling has to be done. Suppose if you have a coal seam, okay, once the seam is beginning and ending, then easy to determine when we can tell the drilling crew, okay, you can stop this coal. But hydrothermal deposits are, it will, it will play hide and seek. It will give the, at once when we think that the deposit is over, when we think, okay, here is a percentage is coming down, percentage is coming down, so now we can close this borehole. No, after some time they may again show up. They are very erratic. That is why I said the geologist role is very important. It's a judgment call when to do. Okay. So that's the reason the hydrothermal deposits are difficult to explore. Then we are ready for reserve calculation. That is the ultimate goal for this exploration. We're ready for the reserve calculation. So there are different methods. There are polygonal method, triangle, inverse distance, cross section, all kinds of geostatistics. And thanks for the the packages, reserve calculation packages for these days. So the geologist role is slightly reduced and made easy. So the estimation of ore reserves may be explained as determining the quantity of economic mineral deposit and the ore in the ore. In fact, determining the grade and thickness is also part of the reserve calculation. Okay, the simulation now, I already told, but I have to come back to this thing. So what I did for the simulation is I took a map roller, paper is rolled along this one, and then I map roller portrays a drill course. I logged the core. When I logged the core, so this is what I found. Then I used that map. I have not even analyzed yet. This is what I found. So now I split the core. So I split the core and I get two halves. One half I retain in the for the future record. On the second half, this is the same thing. Okay. On the second half, I divided and made the samples like this one. I based on the degree of intensity. They were crushed and then sent to lab and they got the results. The weighted average of mineralized ocean, this borehole is calculated. So this is how one single borehole is calculated, and that is the data. I use the same data is for the simplicity's sake. Okay. And then I got the one. Here is the thing. This is an important stage again. To calculate those, the following factors are assumed. Now this is the borehole, hole number one. Then I have to select a few borehole 2, borehole 3, borehole 4. I need at least about 40 boreholes to drill to get the reserve calculation. So three more, 1, 2, 3 hypothetical boreholes are considered. And this dotted zone is the mineralized zone from these three holes. Now here I'm making an assumption not most any geologists, they make this assumption that in this hole, the mineralized zone is will be there, prevailing there till the half of the distance from this hole to that hole. This is the half distance. Same thing from this hole, the mineralization is extends from half between these two. The dotted patch is mineralized ore. So like that, I can do that. Here is the difficulty or danger in presuming that it goes like there. So hydrothermal deposits are erratic, and then they may pinch out, they will go. So suppose if this did not go through half, only went through this part. Oh, I have to use this. Sorry. Okay. So here is this whole thing is mineralization. Okay. And this whole, the assumption is this will go to half, and this half is there, and in this hole it will go to half. What is it will go to half? The mineralization of half. And that is my presumption. This is a very common practice in the geological mineral ore reserve calculation. But like I said, if it is a bedded deposit, this whole thing is one big bed. There's no problem. If mineralized started here, ended here, and there won't be happen coal, for example. But coal also seam 1, seam 2, coal. That's simplistic. This is the one. Bauxite. Bauxite, of course, there's no one layer of bauxite, second layer of bauxite. So once once we reach the unmineralized rock, I can tell the geologist could tell the drilling crew, okay, stop the borehole. But here it is like, so what will happen? In my example here, I calculated the zone is extends half here. This zone extends the half. This zone extends another half. And this extends half. So what is happening like that? But there is no guarantee that this half will extend into half. That half now maybe pinch out like this. This will pinch out like this. What is happening between these two? Reserve calculation, it's calculated the whole thing, but that is not the whole thing. But this is pinched out, this is pinched out. The middle area is we are considering in the ore reserve, but it is not there. Like that. That is why I keep saying that the role of a geologist is very hard. So it's a judgment call how to do this one. So that is what this is. And then, okay, width of the sample is copper percent. Ore reserve calculation. Another assumption is that the width of, okay, that's all. So now for the ore reserve calculation, we need volume. Volume of each block. This is one block. That is one block. From there to here, this is one block. From there to here, that's another block. So the volume of each block is calculated by the end area formula. So I just have 15 minutes. 15 minutes, 10 minutes. Oh. Okay, subsequent the calculation, So what I said, we have to calculate the volume. The cross-sectional area is average multiplied by distance. So now we have to volume, but we need to find out weight. How many tons of ore is there? So the cross-sectional area is average multiplied by, let us say, one section area. Area is easy to calculate there. One section of area, and the second section of area one section of the area and the second section of the area. So we say that combined and divided by 2. So arithmetic average you are calculating, average area. Okay. Then the volume is average area and average and length between cross sections. Average area and length between cross sections. So that gives the volume. Then the tonnage factor provide for the convenience for volume weight. So in the English system or in the English system, the tonnage factor is normally expressed as a cubic feet per ton of ore. How much per ton of ore, how many cubic feet is occupied? So that, so and in the metric system is simple. Tonnage factor is multiplied by the specific gravity of copper. So those are the two methods. Okay? Where so that tonnage factor gives the provision to norm express in cubic feet per ton of ore. That's all. Finally, that is what we need, right? And how much ore is there in the bottom. So we calculate the area, multiplied that the, each section, arithmetic average. So we get the divide by 2. We get the how much ore is there, how much of the material or each section is there, and then we can find out from the uh, tonnage factor. Okay, that is the in the conversation from volume or weight. In the English system, the tonnage. Okay, I told you already. So that's what is the. This is the story of calculating the result. Now, why I am saying this is important, like I already told, most of the universities and colleges, they explain exploration, they stop once they divided the theory that I told. But then this practical, this simulation, I want students and teachers to understand and utilize this process. You can make a, actually I brought some things. I thought that maybe there will be many students and I will give a group of them to imagine and come up with something like this one. But that's not possible here. Okay. If it is 10 minutes, then I have to rush through. Project-based teaching and project-based learning. Students may think, what this has got to geology with this one. This has got this project-based teaching and learning can be used in any field, history, or any other things. Okay. So method enables students to think critically and collaborate with peers. So this is a group, student-centered thing. Then they have to do a thing. So for example, let's say I should do this one, for instance. I talked about all this drilling, core and all that. But if I do this one, make a group of students and I show this, and I will ask them to assume. You don't have to do exact thing. You assume, you presume, okay, this is the mineralized zone rock, then this is this grade, increased grade. So you imagine and you come up and do this. So that's a project. So the project-based learning is theory, what you learn and implement in the field. For geological mapping, for example, is a good example of a project-based learning. So the theory is given, and then the students go to the field and they will use their theoretical knowledge and they do the map. There are many places in the geology to use that one. So what is that happening in a group work? So 21st century, they develop critical thinking and then collaboration. This is not a single person tool. There with other students, they do the collaboration and then creativity and independent learning. So it has got it has got profound impact on colleges and career readiness in geology, in many instances, will PBT and PBL will take place. It has gotten very important. You come up with it when they go for employment, the interview. If they say that I have learned this simulation, I know not just the theory, I know how to do this practice. This is what geologists use in companies. So I have come up with I learned the simulation and I did this one. And also I learned about the PBL and PPT. So then they will, this again, this project-based learning is an important concept. So the combination of that, their resume will have more weight than others. Okay, and then here is the I thank for all the attending this presentation. Sorry, no attendance there. I thank the sponsors of this conference, and I appreciate the conference planning team. Over the months, they have very patiently answered my questions, and I got benefited with that. So that is the answer. Thank you.
Thank you very much. It was, for me personally, it was very, very interesting because I'm an electronics engineer and didn't hear until now from all this. I don't know if there are questions from your side or remarks.
The only remark I can give is the most part of your presentation is amazing, but it's not my expertise. So yeah, but the whole part. But I guess like at the end of your presentation, like you just said, project-based learning and project-based teaching on the point, and the tool you were using, it just seemed like maybe a good starting point before like teaching your major in your discipline. But for me, I guess. That would be the only remark that I can give, but I really enjoyed this whole presentation. Yes, thank you.
Well, thank you.
Yes.
You're a geology student? Or?
Actually, my expertise is like computer science.
Oh,
yeah,
okay.
So yeah, it's actually like another field, but still, I guess we share some like thinking about PBT and PBL. So yeah.
Okay.
It's always good for me to learn something new. So yeah, I appreciate this. Yeah, your time.
How many students you have every year? 10 or 100?
No, I retired and
it's a university in,
yes, I taught physical science and geology, and they are undergraduate students. There in the class there will be about 30-40 students. Yeah, that's the thing. I enjoyed. Actually, I skipped one section of this. The mineral exploration in the field is very interesting. I don't know how the mineral exploration teams work in the United States. I saw one commercial saying one agency, just like they cater in the food and all that here, they advertise that they will come and they will set up camps with a tent, with camps, and then they will take care of the preparation of food and serving and all that. But those are big projects, big camps. For example, in my exploration, where normally we are two geologists, a surveyor, like that, three in the geological camp, and in the drilling camp, same thing. There are about half a dozen people. So that is all. There's no social life normally there. So after that, we will work with the maps and think of tomorrow's project, what it is, and then we come in the evening and then we play badminton, and then sit around and talk. That is, and sit around and talk about it. Partly, okay, with the drilling people, I will tell them, look, the drill core percentage. When they give the drill, they will say 3 feet of this, and we will measure how much is recovered. Only 25%, 30%. What is the reason for that? Maybe the rock is crumpled. All that we'll discuss all those things. And finally, the day we will end with a scotch and around fireplace.
Okay, once again, thank you very much. Unfortunately, they told me there's now another
Okay.
our session. Wish
Thank
you
you.
all the best. Thank you very much.
Thank you
It
very
was
much.